Every time you open a website, stream a video, or send a message, your device sends a request to another machine somewhere in the world. But how does the internet know where to deliver that request? It doesn't use names, it uses numbers, and those numbers are called IP addresses. But what even is an IP address? Where did it come from? Why are there two versions? And what happens when we run out again? Let's break it all down, from how IPs work and why they were created, to what they reveal about you, how governments and companies track them, and where this whole system is headed. This is the digital lens, where complex tech becomes simple. Today we're diving deep into the invisible coordinates that power the modern web. IP addresses. You've seen them in settings menus and router screens, but few understand what they actually do. By the end of this video, you'll understand how IP addresses power everything you do online, and why knowing how they work puts you ahead of 99% of internet users. Why IP addresses exist. Let's rewind to the 1970s. Back when computers were the size of rooms, and the internet was a military experiment called ARPANET. At the time, there was no global addressing system. Each computer talked to another using pre-configured host files. But this system didn't scale. It was clunky, slow, and centralized. Engineers realized they needed a better way, a universal protocol to assign every device a unique address, something that could handle thousands, eventually millions, of machines. This is how the concept of the Internet Protocol IP was born. It gave every connected device a unique identifier, like a phone number for the internet. Without IP addresses, the internet simply couldn't route information. Everything you do, from opening a website to watching this video, starts with your device shouting out to the world, "Hey, here's my IP, send it back here." IPv4, the original address system. The first version to go global was IPv4 Internet Protocol version 4, introduced in 1981. It used a 32-bit system, which sounds technical, but here's what it means. Each IP address is broken into 4 numbers separated by dots, visual shown. Each number can go from 0 to 255. That creates roughly 4.3 billion unique combinations. At the time, that seemed infinite. The internet was academic, military, and niche. Who would ever need billions of addresses? Fast forward to today. Your phone, laptop, tablet, TV, fridge, car, thermostat, they all need IP addresses. We didn't just burn through those 4 billion. We exploded past them. How we stretched IPv4. Engineers bought time with tricks. The biggest one? NAT, Network Address Translation. It allowed multiple devices inside a private network, like your home, to share a single public IP. Your router holds that IP and manages traffic inside your home. It worked for a while, but it wasn't sustainable. Global services, cloud computing, the Internet of Things, they demanded more direct, scalable addressing. So the next evolution was born. Why IPv6 was created. IPv6 came from necessity and vision. Designed in the late 1990s, it uses a 128-bit system. That's not just more addresses. It's 340 undecillion addresses, enough to assign an IP to every single atom on Earth and still have trillions left over. An IPv6 address looks like a long string of alphanumeric characters separated by colons. It's long, but machines, not humans, read them. So why haven't we fully switched yet? Why IPv6 isn't fully deployed yet? The answer is infrastructure. Most of the world still runs on systems built for IPv4. Routers, firewalls, applications, DNS setups. Upgrading everything is expensive, and there's no direct monetary incentive. So we run dual-stack systems, both IPv4 and IPv6 in parallel. The transition is slow but steady. Today, around 35 to 40% of all internet traffic is IPv6. Google, Facebook, Netflix, they're already optimized for it. Could we run out again? Technically, yes. Theoretically, not in the next few centuries. IPv6 provides so much address space that even if you gave every person on Earth trillions of IPs, you'd barely dent the supply. The bigger challenge won't be running out. It'll be building systems fast enough to use them. What's inside an IP address? Let's decode an IP. Whether IPv4 or IPv6, each address includes 2 major parts. Network identifier, where is the device located? Host identifier, which device within that network? In IPv6, we also get prefixes, interface IDs, scopes, for limiting which devices can talk. It's like a detailed mailing address. country, city, street, house number. How devices get IPs. There are two ways: static, manually assigned and doesn't change, used by servers, cameras, systems that must always be found. Dynamic, assigned automatically by a system called DHCP. This is how home networks work. Your ISP lends you an IP for a few hours or days. Dynamic is flexible, static is reliable. Private versus public IPs. At home, your laptop has a private IP, something like 192.168xx. But when it talks to the outside world, your router uses your public IP. This is managed using NAT, and it's one of the most crucial hacks in internet history. Without NAT, the IPv4 shortage would have hit decades earlier. Your public IP is how websites see you. Your private IP is how your home devices talk internally. How routing works with IPs. When you click a link, your device first asks a DNS server, "What's the IP for this domain?" Once it has the IP, your request is routed through a series of networks. Each router reads the IP header and decides where to send the packet next. Eventually, your request hits a data center. The server responds, and the data travels all the way back to your device. If you haven't seen our video how websites actually load, go watch that next. It explains exactly how this invisible handoff works behind every click. Can IPs be tracked? Yes, but not like in movies. Your ISP knows exactly what IP you were using and when. Websites log your IP to track traffic, users, and region. Law enforcement can subpoena ISPs to link an IP to a person. But your IP alone won't give someone your name or address. It shows a region, often down to the city, not your house. Common IP myths busted. Changing your IP doesn't make you anonymous. VPNs help, but don't erase your activity. Private IPs can't be accessed directly from the internet. IPv6 isn't faster than IPv4, it's just bigger. The future of IP addressing. As more of our world connects, from smart cars to smart cities, IP addressing becomes not just infrastructure, but identity. In the future, we may see dynamic location-based IPs, AI-controlled routing layers, new versions of IP protocols based on quantum networks. Your IP is your digital footprint. As tech grows smarter, understanding that footprint becomes part of protecting yourself. Now that you understand how devices are identified across the web, next week we're going deeper into cloud computing. We'll explore how companies like Google, Amazon, and Microsoft run thousands of invisible servers that host your files, apps, and data, and what that means for control, privacy, and power. This is The Digital Lens. Subscribe if you want to master how modern tech really works, one layer at a time. Want to protect your IP or see how websites see you? Check out VPN IP Lookup Tool. The link's in the description and pinned comment. Full breakdown is live on the channel homepage. Just search The Digital Lens. What are IP addresses? IPv4 versus IPv6 Simplified.